Okay, before we start this analysis, I would recommend some books for dynamics of structures. So I'd like to recommend the book from Dewey H. Hodges, and the other author is G. Alvin Pierce. The title of this book is Introduction to Structural Dynamics and Aeroelasticity. Other book I would like to recommend is the book from J. L. Umar, with title Dynamics of Structures. Especially important for vibrating beam we are going to do. Another book can be from Ray W. Cloud, also with the name Dynamics of Structures. And maybe a last one I can recommend to you is the book from Anil K. Chopra, Dynamics of Structures. But this one is more applied to earthquake analysis. Okay, so at least it can be good for the introductory aspects of the dynamics of structures. Okay, so I think we can start. We can start our lecture today. So today we are going to start a new topic. Well, eventually not new for you, dynamics of structures. We are going to do a quick review of vibrating beams. You did that already in year 2 or not? Dynamics of structures. You did? Okay, it's a quick review because it's important for aeroelasticity, okay? So we still have, so this is week 8. So we still have 5 weeks, right? Well, this week and 4 more weeks. So we have a lot of time, so we are going to do revisions eventually in the last week, but also in week 32 we are going to do more revisions as well. So, all right, so let's start with the analysis of beams, dynamics of beams. So imagine you have, for example, a beam. Let's say, for example, a clamped beam like this. You have some distributed load on the beam, something like this. Yeah. We can say that this distributed load is represented by this generic Q, which will be a function of the x. So the x-axis is in this direction, but it will also be a function of time. So we can say, okay, which is something that happens in the aircraft, right? So imagine this distributed load as the lift on the wing. that lift can change with time. Yeah? So this distributed load can change with the coordinate, change along the longitudinal direction of the beam, but it also can change with time. So we are doing a dynamic analysis now, so we need to involve the time element on this, right? What we are going to do now is we are going to focus on an infinitesimal element of this beam. Let's say this very small element of the beam with an infinitesimal length dx, right? So we are going to look or zoom in into this element, and we are going to write on this element what are the forces, moments, and then we are going to use the equilibrium equations, something you learn in year 1, and try to obtain basically the equation of motion. Yeah, that's what we are going to do. And then after getting this equation of motion, we are going to see how we can solve that equation of motion for different boundary conditions of the beam. Clamped or pinned or pinned with a spring on the other hand, or different boundary conditions. Well, we are not going to do all of that today. We have no time. But what I want to show you today is just one example. For example, pinned beam. And I hope I have time to show you today as well how to use a numerical method, which says something we're learning now in FEA and CFD. How to use a numerical method to get a solution for the equation of motion, okay, of this beam. All right, so let's look at this small element. So I'm going to zoom in this element here now. Imagine this is my element with length dx. Okay? This is that element of the beam with my length dx. So this element of the beam will have a distributed load here on the top. This is my qxt, right? And then we will have, I think you remember from year 1 in statics, when we did the bending moment diagrams and the transverse shear force diagrams. This side of the beam will have a transverse shear force V. Yeah? And it will have a bending moment M. But when you move to this wall on the right hand side here, which is separated from the wall on the left by a distance dx, what is going to happen is the transverse shear force now is downwards and equal to the same V that you had here, but because there was a change during this dx distance, there was a change in the loading, we need to say that this V will be equal to the V on the left hand side plus something else, and that something else we will write like this. So this, we can say this term here is a delta V, or a variation in the transverse shear force when I move from the cross section on the left side to the cross section on the right hand side. There is going to be a variation on the transverse shear force. Yeah? And we do the same thing for the bending moment. We will also have on this wall a bending moment, which is going to be equal to the bending moment of the cross section on the left hand side, plus a delta M, which we will represent as the derivative of M in order to x times dx. Okay? So, of course, that if you don't have this distributed load here, you will have at the end something like this. I'm going to very quickly do it here. You will have V on this side and M here. And on this side you will have V and M like this, right? The reason why they need to have these orientations, this transverse shear force and moment, is if you do summation of forces in the y direction, you get V minus V, and this is equal to 0. The forces are in equilibrium, right? If you do the same for the summation of moments, you get minus M plus M, which is equal to 0. So they are in equilibrium, right? If you do summation of moments about this point at the center, for example, right? Let's say point O. In fact, you get something more. In fact, this is not 100% correct, because there needs to be a change on the bending moment. There is no option here, otherwise you are not for example, if you calculate the moment about O, you will have M plus delta M minus dx over 2 times V plus, minus dx over 2 times V. And this is equal to 0. So from this equation, you can calculate the increment on the bending moment when you move from the left-hand side to the right-hand side. Anyway, this is not the part we will be focused on, because we are considering the more general case. We are considering the more general case where the beam has a distributed load like this one. So this is the most general situation when we move from the cross-section on the left-hand side to the cross-section on the right-hand side. There is an increment on the transverse shear force, and there is also an increment on the bending moment. Okay? Don't forget that this is my x direction, longitudinal direction of my beam, yeah, as you can see here. And this is going to be my y direction. And we are going to say that this beam is having a deflection that we will call, that deflection will be along the vertical axis. We will say is given by this V letter, okay? So positive deflection, same as the positive y-axis. Negative deflection is when the beam is going downwards, negative to the y-axis, all right? All right, so what we are going to do now is, first let me try to make this a bit smaller. I'm struggling here with space. What I'm going to do now is to apply Newton's second law. I'm going to say summation of forces in the y direction of my beam in the vertical direction needs to be equal to the mass times acceleration, which I'm going to say acceleration. So if you want, the acceleration is going to be the second derivative of the deflection in order to time t2. Yeah? Or in our scheme, I'm representing with double dot. So this is Newton's second law for the forces. And we need now to take into account all the forces we have in the vertical direction. So we have, in the vertical direction, we have V which is this force here, minus all of this force on the cross-section on the right-hand side, so minus P plus dP dx. There's dx. We have the distributed load we need to include, so plus. So distributed load is a force per unit length, so I need to multiply this force per unit length by the length, which in this case is dx. You all agree with me? So that I will have a force at the end. And this needs to be equal to the mass of this infinitesimal element of the beam. And that mass, I'm going to say, is equal to the density of the material times the area of the cross-section times the length, which is dx. So if you want, this is going to be my infinitesimal mass of that element, right? And I just need now to multiply this mass by the acceleration, which is v double dot, right? So if you look carefully here to this equation, there are some things that cancel out. For example, this V cancels with this V, this transverse shear force. So what I'm going to do is I'm going to send, let me copy this to a new slide. I'm going to send the mass times acceleration to the left-hand side. And then we'll get at the end something like this. Minus dv dx times dx, which is this term here. Now I'm going to send the mass times acceleration to the left-hand side, so we will have minus the density times dA, which is the area of the cross-section, times dx, times, I'm going to write this way, the second derivative of the deflection in order to the time, and the external distributed force I'm going to send now to the right-hand side. It will become minus q xt times dx. Right? So nothing special I did in this step. I'm just organizing the terms, simplifying a bit. Some terms cancel here. I can simplify even a little bit more. If you look carefully, if I divide the left-hand side and right-hand side by dx, these dx, they cancel, right? So I can make it even a bit more simple. So at the end we will have minus the derivative of the transverse shear force in order to x, minus the density times the cross-sectional area, times the second derivative of the deflection in order to time, is equal to minus qxt. And this is one first result that we obtain. So you get here a partial differential equation, right? Where you have one derivative involving the x coordinate, or a spatial derivative, and we have a time derivative, a second derivative, in fact, for the deflection. So, but this is not the end yet, because what I'm going to do now, so far we have only used the equilibrium equation for, or the Newton's second law for the forces in the vertical direction. So I'm going to copy this figure and because what we are going to do now is to use, we have more equilibrium equations. We have the equilibrium equation for the moments, right? So what I'm going to do now is to do summation of moments about a point on this cross section on the left hand side. So I'm going to do summation. So let's call this point, for example, point O, right? So summation of moments about this point O needs to be equal to the moment produced by the mass times acceleration, or the moment produced by the inertia force, right? Which is the mass times acceleration. So we will have, for these elements, we can write like this. We will have in the center of gravity of this element, which is at dx over 2, yeah? You agree with me? We will have this force here in green, which is our dm, the mass of this element, times the second derivative of the deflection in order to time. So I need to say this summation of moments about point O needs to be equal to the moment produced by this inertia force in green that you have there about point O. And that moment is 1 over 2 dx. This is the distance in the perpendicular direction to the line of action of the force. And then it multiply now this by the force, which is dm is rho, the density, times the area of the cross-section, times the x, times the second derivative of the deflection in order to time. Okay? And in an infinitesimal analysis like the one we are doing, whenever we have dx square, like we have here dx times dx, that will give dx square, we ignore this term. So this term is going to be very close to 0, so we can say for this infinitesimal analysis, this summation of moments is going to be equal to 0. Because I can write here, because of dx square. Right? So it's there, so you don't forget why we are. So this is again still the Newton's second law now for the moments. Summation of moments equal to the summation of moments produced by the inertia forces, right? We are, of course, in this case, neglecting the rotational or the angular acceleration of the beam. Okay, so we are only considering the linear acceleration along the deflection direction of the beam. All right, so if you now get all the moments you have, if you do that balance, you get minus m, which is this moment here. You get m plus dm dx times dx, so plus m plus dm dx times dx. Thank you. And then we have the moment produced by this transverse shear force here, about point O, isn't it? Which is going to be minus. The force is V plus the derivative of the transverse shear force times dx. This is the force. I need to multiply by the distance to get the moment, so that distance is going to be the x. And we have at last the moment produced by this distributed load, which is going to be plus. So this Q is the force per unit length. I need to multiply by the length, which is dx, to get the force, the total force. In order to get the moment, I need now to multiply by the distance, which is 1 over 2 dx. Right? And that's all we have. So this needs to be equal to 0. And the good thing is, this is the part I like most. Minus m cancels with m. Now we have here dx times dx is going to be dx squared. So I can say this term here will be neglected because of the dx squared. Same thing here, I have dx times dx. I will have dx squared again in an infinitesimal analysis like this. We neglect the squared dx components, so I can say this term is also going to be neglected. So we end up having only this dm dx times dx, and then we have this term here for the transverse shear force, so minus v dx equal to 0. That's all we have. So we can simplify this a bit more. Dx goes away, and we get the transverse shear force equal to the derivative of the bending moment in order to x, which is something that I think I did statics in year 1 for you, right? I remember I talk about this. You can get the transverse shear force from the derivatives of the bending moments. Remember when you did the bending moment diagrams, transverse shear force diagrams for the beam deflection we did? Once you have the bending moments equations, you can get the transverse shear force equation by doing the derivative of the bending moment. That comes from the equilibrium of the moments about point O, right? All right, so let's go back to this equation. So I'm going to copy this equation here. This was the partial differential equation we obtained from the summation of forces in the y direction equal to mass times acceleration. Maybe a little bit smaller. What I'm going to do is I'm going to make use of this. So the reason why I derived this from the summation of moments is because now I'm going to use this equation to replace this transverse shear force I have here. I'm going to replace with the derivative of the bending moment in order to x, right? Nothing more than that. So then we will have minus the second derivative of the bending moment in order to x. So in this step, nothing special. The only thing I did, I just replaced the transverse shear force with the derivative of the bending moment. So we have now a second derivative in order to x, but it's now a second derivative of the bending moment. We are going to do the analysis for free vibrations. Basically, what we are going to say is our analysis will consider the beam vibrating under no action of any external force. So we will say the external force so the right hand side of this equation is going to be equal to 0. And then what we are going to get is the natural frequencies and so it's an eigenvalue, eigenvector problem, right? So we are going to get natural frequencies and the vibration modes, yeah, for the beam. When we, in 1 or 2 weeks' time, when we start doing the flutter analysis, air elasticity, we are going to do the full analysis for forced vibration of the wing, basically, right? But we need to understand first, I think that's why I'm doing this today, we need to understand how a simple beam, what is the equation of motion and how to solve this equation of motion before we go into a more complex analysis for the entire wing, all right? So free vibrations, so no, the right-hand side of the differential equation is equal to 0. We also know from bending of a beam that the bending moment over EI, which is the bending or the flexural stiffness of the beam, EI. I is the second moment of area about the neutral axis of the beam, right? E is the Young modulus. M is the bending moment. So we know that this is equal to the second derivative of the deflection in order to x. This, you did this, I'm quite sure, in year 2 in solid body mechanics. So what I'm going to do is I'm going to basically write the bending moment as being equal to EI times the second derivative of the deflection in order to x. And I'm going now to replace the bending moment in that equation. So this is getting more and more complicated. But, well, I don't think it's getting more complicated because this is something you did learn already from beam deflection. We are just replacing in the differential equation, right? Maybe I'm speeding up. Am I speeding up this too much, or is okay? Seems okay. Right. Good, great. Anyway, this is a quick revision, right? I think you did this already. So this is a revision of this vibrating beam. All right, let's replace that. So we will have. So if I replace, so we will have EI. Now I will have the fourth derivative of the deflection in order to x. I also multiplied left-hand side and right-hand side by -1. And this is the final differential equation, or if you want, we can put this we can divide everything by EI, which is more convenient here because of the fourth derivative of the deflection. So we will get something like this, rho dA over EI okay. So this, as you can see here, now, for example, if you compare these two equations, this one with this final one we obtain, now the second derivative in order to time is the second derivative of the deflection, and the fourth derivative is also of the deflection in order to x, right? While in the equation in the top, we have a second derivative of the bending moment and a second derivative in time of the deflection. So this is the differential equation. This one here at the bottom is the differential equation. We are now going to try to solve it. All right? So this is the differential equation of motion of the beam. So we need to get when I say we are going to try to solve it, is we are going to try to find a solution for the deflection. Deflection is changing with the position, longitudinal position on the beam, and changing with time. Right? This is a dynamic problem. And the way this deflection is changing is governed by this differential equation here. So we just need now to solve this differential equation. And that's what I'm going to try to do it. So by the way, I have these notes I did myself. I will upload these in Blackboard, all right? So I'm just following these notes to make sure I don't miss anything. But I will upload the notes in Blackboard. All right. So let's see how we can get a solution. So let me copy this differential equation here. This is our differential equation. Okay. Right. So, like I said, we are going to be looking for a solution in the form, so a solution for the deflection. And we are going to do this way. We are going to consider one component, xi, which is going to be only a function of time. So our deflection depends on two variables. One is the longitudinal coordinate x of the beam. So depending on the longitudinal, or depending on the cross-section you are on the beam, the deflection will be different. It's quite obvious, right? If you have a beam deflecting, imagine it deflects like this. If you are in this cross-section, we'll have one deflection. If you are in this, the deflection is going to be different, right? So it makes sense to say that our deflection depends on the longitudinal coordinate x. It also makes sense to say it depends on the time, because this is a dynamic problem. So at instant 0, that this cross-section might be at this position, but at instant 1 second, for example, it might be with some deflection there, right? So it's changing with time as well. So the deflection will have a component, this xi, which is only a function of time, and it will have another component, phi, which is going to be only function of the longitudinal coordinate x. All right? So we are basically, what we are doing is, for the solution for the deflection, I am splitting the time and the longitudinal coordinate into separate functions. One, xi, only function of time, and the other is phi, only function of x. All right? And then what I'm going to do now is just I'm going to replace in my differential equation here at the top, where I have v, I'm going to replace with xi times phi. So I need to do the derivatives and replace, right? So let's start. Let's start with the derivative. So we can maybe do it here. Derivative of the deflection in order to time, the first derivative. So is going to be equal to what? What do you think? Is going to be equal to, I can say, the derivative of the deflection in order to xi times the derivative of xi in order to time, isn't it? The chain rule for the derivatives, which will be equal to derivative of this in order to xi is going to be equal to phi x. Derivative of xi in order to time is going to be equal to xi dot. You agree with this? So this term is this one, and this is the result of the derivative of the deflection in order to C. Right? If I do the second derivative, because I need the second derivative, is what I have in my differential equation, is the second derivative. So the second derivative of V in order to time is going to be equal to phi x times the second derivative of C. Right? So you can do again the chain rule if you want for this. This, if you want to do the chain rule, this is going to be equal to the derivative of deflection in order to C dot times the derivative of C dot in order to time. This term is this, and this term is this. Right? So this derivative is done, the second derivative of the deflection in order to time, but we need the fourth derivative of the deflection in order to x. So let's speed up a little bit, otherwise this becomes a bit boring. We don't want that. So the first derivative I can do in the same way the derivative of the deflection in order to phi times the derivative of phi in order to x. Chain rule. So this is going to be equal to the derivative of this in order to phi is C. The derivative of phi in order to x is going to be, I'm going to do phi prime x. So this phi prime, if you want, is the derivative of phi in order to x. All right? To make it clear here. Okay, so the fourth derivative of the deflection in order to x is going to be equal to C times the fourth derivative. Oh, you have 4 primes there of our phi function. So this 4 primes means equal to the fourth derivative of function phi in order to x. Okay? So we have all the derivatives we need, just going to replace the derivatives in the differential equation. So the fourth derivative is this one. I'm going to copy and put it here. Oops. So this is the fourth derivative of the deflection in order to x. Now we have plus rho dA over EI times the second derivative of the deflection in order to time, and that is given by this term here, which I can copy. Copy and paste. Right? And this needs to be equal to 0. All right, so what I did was, the major step here was this one. I think, for the solution for the differential equation, we are assuming that our deflection is going to be given by a product of two functions. One function, xi, is only depending on the time. The other function, phi, only depends on x. They are separated functions, right? And then the only thing I did now was just to do the derivatives. And I'm replacing now the derivatives in the differential equation. And if you do that, you get this. And what I'm going to do now is just to manipulate this equation in order to have on the left-hand side the terms that depends only on the x coordinate, and on the right-hand side the terms that depends only on the time variable, right? So if you do that, you will get something like this. Phi 1, 2, 3, 4 square over phi x, yeah, equal to minus rho dA over EI times xi double dot time over xi function of time. Look at this. So the only thing I did, so basically I sent this guy to the right hand side, and after doing that I sent phi x to the denominator here. That's what you have here. Anyway, this is quite trivial stuff. But the important thing we have is, as you can see on the left-hand side, we have only the terms depending on the x coordinate, while on the right-hand side we have the terms depending on the time, the acceleration, and it's not deflection, it's the xi variable, right? So they depend on different variables. One is x, the other is the time. So how can they be equal? The only way they can be equal, don't forget you have an equality here, right? The only way this can be equal is if they are equal to a constant. And I will call this constant alpha. Right? It's the only way I can have this equation valid if they are equal to a constant. And of course, this constant alpha cannot be equal to 0, because otherwise we'll have a non-dynamic problem, right? The beam is not vibrating, right? So that is the constraint you need to have on this constant alpha. It cannot be equal to 0. The good thing about this is that it will give us, for example, if you look at this first equation here, involving only the xi variable, function of time, you can write this equation something like this. You will have minus rho dA over EI times xi double dot function of time equal to alpha xi function of time. So you can send this guy to the left hand side, and then you will get something like this. Rho dA over EI plus alpha xi t equal to 0. Or if you divide everything by rho dA over EI, you get this equation here. You get xi double dot plus alpha EI over rho dA times xc function of time equal to 0. Yeah? So you have this equation here, which, as you can see here, the only thing you have there is this function xc, which is function of the time only. The x, the phi function is not here, right? And then if we go a bit deeper on this equation here, the solution for this equation is in the form of sine and cosine. So sine of Wt, W is the frequency, T is time, plus B times cosine Wt. I think this might be familiar to you from the maths models you had in year 2 and 1. I think you did study some techniques to solve differential equations, right? Partial differential equations. So that's what we are doing here. So the way we do this is by assuming a solution for xc in the form of a combination of a sine and cosine. In that sine and cosine, you have the frequency, W, and you have this A and B, which you calculate from, so I can write here, this A and B you calculate from initial conditions. Okay, so there are constants that come from initial conditions, but let's see if we really need this A and B for the analysis we are doing. Look at what I have to do now is just to get the first and second derivative of my function xc. The first derivative is quite easy. It's going to be AW cosine Wt minus BW sine Wt. Right? I'm just deriving a sine and a cosine function. If I do a second derivative, I will get minus AW square sine Wt minus BW square cosine Wt. Or, if you want, this is going to be equal to minus W square Ct. Right? You agree with me? So Ct is this equation here. If I multiply xc by minus W square, I will get xc double dot. And the good thing is that now I'm going to replace double dot xc with minus W square times xc in my differential equation and see what is going to happen. So I'm going to copy this to another slide. So if I do that, I will get minus W square xc times time plus alpha EI rho dA xc times time equal to 0. Look at this now. This xc cancel. If I divide the left-hand side and right-hand side by xc, I get rid of this xc function. And then my conclusion is my W square is going to be equal to alpha EI over rho dA, or if you want, my natural frequency of the beam is going to be equal to square root of alpha EI over rho dA, which is a very, very important result, which I think you are familiar when I think last year with Chris Myers, he did vibrations, right? Spring and a mass, right? You remember you calculated natural frequency of a spring and mass system, right? You obtained for that spring and mass the natural frequency as being the square root of the stiffness of the spring over the mass. Remember this from year 2 vibrations? A very simple 1 degree of freedom problem, spring and a mass. So if you look carefully what you have here on the numerator, EI is the flexural stiffness of the beam. Rho dA is a kind of a mass, right? So you have something quite similar with that, but not exactly the same, of course, because different problems, right? Okay, so we get natural frequency, so we get the solution for the natural frequency, but so once you get this solution, you can go back to this equation here. You can go back to this equation, replace your frequency with the one you obtained, and then get A and B from initial conditions, or initial velocity, for example, of the beam, or initial deflection of the beam, initial conditions, and then you can get this function xi, right? But we still have to work out our function phi. So if we go back, to this formulation here, when I said that this equality needs to be equal to a constant, so we have only used this equation for our analysis. We are going now to use the other part to get our function phi, all right? So we are going to do that so we are going also to assume a solution for this function phi that is a bit more difficult than the previous one. So this one here is quite standard, this solution. The solution for the phi function, depending on the x coordinate, is more complicated. So we are going to assume a solution in this form for phi x. d1 sine of our constant alpha times x. This constant alpha is this one here. This one here, right? Plus d2 cosine of alpha x plus, I'm going to continue here, d3 hyperbolic sine of alpha x plus d4 hyperbolic cosine of alpha x. All right, so we are going to assume a solution in this form involving sines, cosines, and hyperbolic sines and hyperbolic cosines. These d1, d2, d3, d4, so if you want d1 to d4, they are obtained from the boundary conditions. For example, if a beam is clamped, or with an hinge or pinned, or a free edge, you will have different boundary conditions, and that will allow us to calculate these four constants. Let's do an example for the most simple one, which is the pinned beam, okay? Let's do, so basically we will have a beam with these boundary conditions, right? Let's say, for example, the length of this beam is L, generic length L, for example. Okay? Let me just make this a bit smaller to find some space. This as well. This can in fact go here, right? And then I can move all this stuff. Make it also smaller and move it here. Right. So we will have this. So the good thing is that, so let's say this is my longitudinal direction, x. My y-axis is here of my beam. So I can say that for x equal to 0, so my boundary conditions will be something like this. For x equal to 0, I am at this point of my beam, right? I need to say the deflection V for x equal to 0, so deflection V at 0 t needs to be equal to 0. You all agree with me? Because there is the support there. So this needs to be equal to 0. And if you write the deflection as the product of your xi function, which is this one, times your phi function, which depends on the x coordinate, which in this case is 0, this needs to be equal to 0, right? So look at this. When I use that boundary condition of the beam, I need to replace here in this equation where I have x with 0, right? So I will have to get from this equation my phi of 0, which is going to be equal to, if I replace here this x with 0, I get sine of 0, which is 0. If I replace here in the cosine, I will have cosine of 0, which is 1. So I will have d2 hyperbolic sine of 0. If I replace x by 0, again, I will have hyperbolic sine of 0, which is 0. Yeah? Don't forget, the hyperbolic function is something like this. It passes on 0 when x is equal to 0. And, by the way, the hyperbolic cosine is something like this. This is 1. Okay? So, going back to our problem. Now, if I replace here x by 0 in the hyperbolic cosine, I get hyperbolic cosine equal to 1. So I will get d4. d2 plus d4. And this needs to be equal to 0 because of the boundary condition, or because of the support. The deflection at that point is equal to 0. So we get this equation. We need to keep it. We are going to be looking for these d1, d2, d3, d4 constants, right? The other boundary condition we have for x equal to 0 is the moment. So, do I have any moment at this point of my beam? No, the beam is not clamped there, right? It's allowed to rotate about that point, so there's no moment as reaction. So the other boundary condition we have is the moment for x equal to 0 is going to be equal to 0. But the moment is given by this equation, EI times the second derivative of the deflection in order to x squared. Which means is going to be equal to EI times CT times the second derivative of my function phi and calculated at point 0. And this needs to be equal to 0. Is the boundary condition for the moment for x equal to 0 being equal to 0. So I need to get the second derivative of this function in order to x. That's what I'm going to do now. Copy. We are going to do a break soon. Let me just finish this very quickly, hopefully. So the first derivative is going to be equal, so d1 alpha times cosine alpha x. I'm deriving in order to x, right? Minus d2 alpha sine alpha x plus d3 alpha. The derivative of the hyperbolic sine is the hyperbolic cosine hyperbolic of x. And let me move this a little bit. The last one is plus d4 alpha hyperbolic sine now of alpha x. This is the first derivative. The second derivative, I need to derive the equation above one more time. So I will get minus d1 alpha square sine alpha x minus d2 alpha square cosine alpha x plus d3 alpha square hyperbolic sine alpha x plus d4 alpha square hyperbolic cosine of alpha x. And now I need to do the second derivative for x equal to 0. I just need to replace in this equation here x, where I have x, I need to replace by 0 and see what we get. So again, sine of 0 is 0, so d1 goes away. Cosine of 0 is 1, so we will have minus d2 alpha square. Hyperbolic sine of 0 is 0. Hyperbolic cosine of 0 is 1, so we will have plus d4 alpha square. And this needs to be equal to 0 because of the moment boundary condition. Moment for x equal to 0 is equal to 0. So this alpha squared goes away, and then we end up having this equation. Oops. What have I done? Okay. It does not go away. It can go away, but I'm making sure it does not go away, because what I want to show you is, so I'm going to do like this. You agree with me? I'm just factorizing the equation above. Then I have two options here. Alpha equal to 0, which cannot happen. The reason is, when I did this equation, I said here, it's clear here, alpha needs to be different from 0. Yeah? The other option we have is minus d2 plus d4 equal to 0, which means d2 equal to d4. Yeah? So, conclusion is, so we have now two equations for two unknowns. The first equation we have is this one, d2 plus d4 equal to 0. So I'm going to write here d2 plus d4 equal to 0. The second equation we have is d2 equal to d4. d2 equal to d4. So if I replace the second equation into the first equation, I get at the end 2 times d2 equal to 0, which means d2 equal to 0. If I replace in the second equation, I get also d4 equal to 0. Fantastic. So for the pinned beam, d2 and d4, they are 0. So this equation here for our function phi is going to be reduced to, I'm going to paste the equation here, is going to be reduced to only the terms containing, d1 and d3, because d2 and d4, they are equal to 0. So I can move this guy now to here. Getting simple now, right? We are getting a bit easier now. Right, so we have used so far two boundary conditions for our beam, the ones for x equal to 0, yeah, for this support, but we still have this support here for x equal to L. You agree with me? So I need to now say that for x equal to L, so I am at the single support on the right hand side of my beam, I will need to have phi for x equal to L equal to 0, because the deflection at that point is not allowed as well. And I will also have, for x equal to L, I have my second boundary condition, which is the second derivative, which is related with the moment. Yeah, comes from here. Look at this. The moment involves the second derivative of my function phi. So the second derivative needs also to be equal to 0. But now the difference is for x equal to L. So if I replace in this equation for phi, which I'm going to make it a bit bigger now, I will have something like this. Phi L is going to be equal to d1 sine of alpha L plus d3 hyperbolic sine of alpha L. And this needs to be equal to 0. The second derivative for x equal to L is minus d1 alpha square sine alpha L plus d3 alpha square sine hyperbolic of alpha L, and this needs to be equal to 0. Okay, I think I have this right. So I'm just replacing, and now I can do something like this. We are almost finishing for the break. So 5 more minutes and we do a break, all right? We are almost there. Look, I'm going to put this in a matrix form like this, where I will have here sine of alpha L hyperbolic sine of alpha L. Below I will have before I do that, this alpha square I can cancel in this equation, so I will have minus sine of alpha L, and here I will have hyperbolic sine of alpha L, and this matrix will multiply my D1 and D3, which are my unknowns, and this needs to be equal to 0. Okay? We have here now a homogeneous system of equations. If you want to avoid the solution D1 equal to D3 equal to 0, if you want to avoid this solution, or the trivial solution, you need to say that the determinant of this matrix, needs to be equal to 0. Remember that? You did that, for example, in solid body mechanics, when you calculated the principal stresses. This is eigenvalue problem, okay? So if you want to get the non-trivial solution, you need to impose that the determinant of this matrix is equal to 0. If you do that, the determinant will be sine of alpha L times hyperbolic sine of alpha L plus sine of alpha L times hyperbolic sine of alpha L equal to 0, or if you want, 2 sine alpha L times hyperbolic sine of alpha L equal to 0. Let's focus on this. This is the result of imposing the determinant of that matrix equal to 0. If you focus on this equation, again, you have two options. One is sine of alpha L equal to 0, or hyperbolic sine of alpha L equal to 0. Let's look at this one first, the hyperbolic sine solution. This is impossible to happen. The only way this can happen is if alpha is equal to 0. The hyperbolic sine is equal to 0 only when what you have in the argument of the hyperbolic sine, or when this alpha is equal to 0. But alpha cannot be equal to 0, so this solution is impossible. So the only option you have is this one here, sine alpha L equal to 0. Is the only option you have. And the answer for this solution is when alpha is equal to k pi over L, where this k is 1, 2, 3, 4, 5, and so on. So for example, imagine if you replace this alpha in these arguments, you will have sine of kappa pi L times L. So this is going to be equal to sine of kappa pi. So sine of k pi. So when k is equal to 1, you have sine of pi, which is 0. K equal to 2, you have sine of 2 pi, is 0. Sine of 3 pi is 0, 4 pi 0, and so on, right? So this is, in fact, the solution for that constant alpha. Remember this constant alpha, you might be forgetting, is when we said here the solution of this, when we separated the variables. By the way, this is the name of the method, separation of variables. We said that this equality here is only possible when it is equal to a constant alpha. So this is the alpha we are talking about. And we know now for a pinned beam that that constant needs to be equal to this, k pi over L, all right? So let's do even let me see what I have here. Yeah, so just one quick thing. If we go back to this solution for the natural frequency that we obtained, this one, which I'm going to copy, or maybe I can copy the square one. Copy. If I did put it here, I can replace now alpha in this equation by this alpha, and then you will get the square of your natural frequency equal to k pi over L times EI over rho dA. So now you can get your natural frequencies. You have everything, okay? You have the area of the cross-section, you have the Young modulus, you have the second moment of area, you have the density of the material you are using. So the lowest natural frequency is when this k is equal to 1. So the lowest natural frequency is going to be the square root of pi EI over L rho dA. This is usually the design frequency. You know, if you excite the beam with a frequency equal to the natural frequency, you get the resonance of the beam, right? You remember that from vibrations you did last year? You talk about resonance, right? So that's why the lowest natural frequency is a very important value to get in the design. You can imagine this on a wing, right? We are going to be looking for the natural frequencies of the wing. So we make sure that the wing is not excited with a frequency close to the natural frequency, so we avoid resonance, all right? So let's do a break, and after the break, I think I will not have time, but anyway, I will try to introduce you. So what we did was the analytical solution of the equation of motion, of that differential equation. I'm going to introduce you a numerical solution for the equation of motion, right? That's what I plan to do after the 5 minutes break, all right? Okay, so let's continue. So we have 25 minutes, so it's not much. So I think I will not have time to finish completely what I want to do now, the numerical solutions, because I don't know if in FEA, you are doing FEA as well, right? Have you started doing the weighted residuals? Did you ever heard about weighted residuals? No? Right, so I think we will have time only. So I will introduce the weighted residuals to you now, but we will not have time to use the weighted residuals for the solution of this beam, vibrating beam, but we will continue next week. Okay, we will continue next week with that. So at least today, I will like to introduce quickly the weighted residuals, which is something you need also for FEA. Okay? So eventually you will be doing this again in FEA, but take this as a kind of introduction to your FEA. We need to have these weighted residuals to get the numerical approximation of the, for example, for the clamped beam. So what we did so far was for a pinned beam, but if you want to do the analysis for a clamped beam, this weighted residuals method is very nicely used on the solution for that problem, okay? All right, so the weighted residuals is, so I can write here, weighted, residuals is a numerical method to solve differential equations, okay? So if I give you a differential equation like this, AU equal to F, where this A is a differential operator it can be a first derivative of u or a second derivative of u or whatever, right? It's a differential operator, okay? So what we are looking for, so u is the exact solution of this differential equation. But in numerical methods, we are going for an approximate solution. So we can write something like this. Approximate solution which is going to be a solution in the form, so I'm going to call that solution u with a hat and with a subscript n. This subscript n is related with the number of terms this approximation will have. So it's going to be a summation here from 1 to n of coefficients that we don't know, ai, times phi I, which usually in FEA is known as shape functions. All right? So this approximate solution is going to be a summation of unknowns, A, I, multiplying shape functions, which we know. For example, when you are doing a mesh in FEA, if you are using, for example, quadrilateral elements, they have known shape functions. Can be bilinear functions in x, y, or quadratic functions. Those kind of functions we know, okay, are given. And then the AI is what we are going to be looking for. So this AI you have here, if we can calculate this AI, because we know the shape functions, we will be able to get our approximate solution, for example, for the deflection of the beam. Yeah? The thing is, how do I get this AI? So what I'm going to do now, look at this. I'm going to go back to my differential equation, and I'm going to rearrange this equation in this form. I'm going to send everything that is non-zero to the left-hand side, and on the right-hand side needs to be equal to 0. Okay? Which is, in our previous analysis, something we had. Let me see where we had this. Yeah, look at this differential equation here. On the left-hand side, everything that is non-zero. On the right-hand side, 0, right? And now, this is the most important step. What I'm going to do now is, instead of using the exact solution for this differential equation, I'm going to replace the exact solution with my approximation. If I do that, I will get A u hat n minus f. And the most important thing now, because this solution un is not my, sorry, what have I done here? Because this un is not my exact solution, this is an approximation, then this aun minus f is not going to be equal to 0, right? It's going to be equal to a small residual. You're starting to understand the name of the method, weighted residuals. So I'm going to say this au hat minus f, which is the result of replacing the exact solution with my approximation, is not going to be equal to 0, is going to be approximately equal to 0. There's going to be a residual number here, not exactly 0, but approximation, close to 0, right? So this term that you have here on the left-hand side, because it's not equal to 0, it's a very small number, it's a residual, we call this the residual. We usually call this by R subscript n. So this n is again related with this number of terms in this summation for my approximation solution. So I will have there a residual which I want to be as close to 0 as possible. The more closer to 0 this residual becomes, it means more accurate my approximation will be. And more closer I will be of the exact solution, right? So how do I make this residual as minimal as possible? So what we do is we multiply this residual by a weight function let's write like this, and I integrate over the entire domain of my body, and then I say this integral equal to 0. Then you understand the full name of this method, weighted residuals. So weighted because I'm weighting, so I'm putting a weight in my residual and making sure that this residual then is the minimum in the entire domain of my analysis. Okay? So it's like having something like this. It's like having a beam. This integral means I'm having a beam, I'm calculating the residual in all these points and making sure that residual is equal to 0. Yeah? So when I do this, when I add the residual at this point with the residual at this point with the residual at this point, I'm doing the integral. Yeah? So let's do a quick example and finish our lecture. So I will finish here and then we continue next week. Let's do a very quick example on a beam. It's a static example I'm going to do now, right? Not a dynamic, but just for you to see the application of the weighted residuals. You have a beam like this, pinned beam again. You have this distributed load on the beam. This distributed load is given and equal to 1000 Newton per meter. This length of the beam is 1 meter. This is my x-axis, this is my y-axis. What is also given is the flexural stiffness EI equal to 1000 Newton times meter square. This is a problem that you know how to solve from year 1. The exact solution, we are not going to spend time getting the exact solution, but I can write here the exact solution for this problem, which is, the exact solution for the bending moment, which is qx over 2, 1 minus x. So you get this from the bending moment equations you learned in year 1. And the bending moment over EI needs to be equal to the second derivative of the deflection in order to x squared. So we have been, this comes from beam deflection. We have been using this before. So where is my differential equation? Well, my differential equation is when I send everything to the left-hand side that is non-zero. So I will get the second derivative of the deflection minus MEI equal to 0. So this is my differential equation for beam deflection. This governs the deflection of my beam. Analytical solution. Well, if you do beam deflection like you did in year 2, you get this analytical solution V. So this is the exact solution we are going to use just for comparison with our numerical results, all right? This is the analytical solution, right? If you do the beam deflection, like you did learn last year, you will get this analytical solution. Now let's use the weighted residuals method. So we are going to start from our differential equation. This is my differential equation. I'm going to build the residual. So my residual is going to be obtained when I replace the exact answer, V, with my approximation, V hat, right? So my residual will be the second derivative of V at subscript n in order to x squared minus m over EI. This is my residual. How am I going to build my approximation Vn, V hat n? Well, I'm going to do summation equal to 1 n times AI phi I. There is one thing I forgot to mention here when I introduced the approximation, which is the same here. These shape functions phi I, they need to respect the boundary conditions of the problem. I told you there's shape functions. We know these shape functions. We define these functions, or we assume these functions. But they need to respect the boundary conditions. For example, look at deflection equal to 0 for x equal to 0. These shape functions phi I, they need to give you 0 when you replace x by 0. So for the case of our beam, this beam, one boundary condition is yes, deflection equal to 0 for x equal to 0, and deflection equal to 0 for x equal to 1. So if I use these shape functions, look at this. When I do x equal to 0, I need to have phi I equal to 0. That is true, because if I replace this x by 0, I will always have phi I equal to 0. So I'm respecting the boundary conditions. What about for x equal to 1, which is the deflection at this support? It needs also to be equal to 0, right? So if you replace in this equation this x by 1, you get 1 minus 1. That will give you always phi I equal to 0. You see? I forgot to mention this, but I'm mentioning this now. So I'm going to build my approximation for V at using these shape functions you have here. But I'm not going to use an infinite number of shape functions. This summation is not going to be equal to infinity. For this example, I'm going to use only 2 terms. The more terms you use, more accurate your approximation will be. This is equivalent when you refine the mesh in FEA or in CFD. When you refine the mesh, basically what you are doing is you are including more terms in this summation here on your approximation function, all right? We are going to see at the end how this works more clearly. All right, so what do I have to do? Well, I need to do the second derivative. So let's do that in a different slide. So we have, this is my, sorry, I should not have copied this one. This one here, the residual. So I need to do the second derivative. So if I'm considering 2 terms in my approximation function, I will have A1 times phi 1 plus A2 times phi2, right? Or I will have my Vn, V hat n, is going to be phi1 is x1 minus x, and phi2 is x squared 1 minus x, and I need to multiply this by A2. With only two terms, my approximation is going to be this. The first derivative, dvn, in order to x, is quite straightforward, right? Is 1 minus 2x a1 plus 2x minus 3x squared a2. I need the second derivative, so I need to derive again the second derivative. Is going to be equal to minus 2a1 plus 2 minus 6x a2. Right? And I need to replace now this second derivative in this equation and get my residual. So in fact what I did, so this needs to be equal to 0 at the end, right? So what I did was I multiply everything by EI. So my residual, in fact, is going to be equal to EI, second derivative, x2 minus m. Okay? So I'm going to replace now the second derivative in this residual, and then you will get something like this. I can copy paste second derivative, and then you will get your residual Rn is going to be equal to EI times, now I'm going to replace the second derivative here. This is my second derivative, minus m, but my m was given is here, right? So my m is qx over 2 times 1 minus x. This is my residual. Okay? Now, I'm going to build my weighted residual. So I'm going to do the integral in the domain of a weighting function times my residual. The problem now is, what is this weighting function here? This weighting function, there are different methods, but I'm going just to talk here about the most used method in FEA, which is the Galerkin's method, all right? So, Galerkin So what Galerkin says is that your weighting function is equal to your shape function. That's it. So how many shape functions do we have in this problem? We have two. We have phi1 and phi2. And we know how much. So phi1 is x times 1 minus x. Phi2 is x squared times 1 minus x. All right? And then I'm going to do this. Look at this. Doing this integral means integral in the domain. So the domain of our beam is from 0 to 1. Yeah? The beam is 1 meter long. So we get integral from 0 to 1. I'm going to use the first shape function, replacing my weight function in my weighted residual. So the first shape function is x times 1 minus x. So this is my phi1, if you want. equal to W1. And this needs to multiply my residual. But my residual, we calculated already. My residual is given by this. I'm going to copy all of this residual, and I'm going to paste it here. Maybe shrink a little bit. So this is my residual. And this integral is done in the x direction. And this integral needs to be equal to 0 because we want it to make as small as possible to minimize our residual. Yeah? We are going to have a second integral, which is when our weighting function is equal to our second shape function phi2. We are almost finishing, just a little bit more. So this second equation, so I just copy-paste the first integral, but now I need to change because now this needs to be x squared, and this is going to be my phi2. Right? And the good thing about this now is that I'm going to have, if you look at this, I have the integrals. So I'm going to have here a matrix, 2 by 2 matrix, where that are going to be multiplying A1 and A2, which is what we are looking for. And this is going to be a non-zero vector. This non-zero vector comes when you do the integral, when you multiply, for example, x times 1 minus x with this term here and send to the right hand side. This is what is going to occupy this place. Yeah? This place here in this matrix is when you do this integral. This multiplied by EI times minus 2. And when you integrate, of course, you need to do the integral, right? That will go into this position 1, 1 in this matrix. Position 1, 2. This one here is when you do this times this times this. And integrate. That goes there, right? So, if you do all of this, you will get a system of 2 equations for 2 unknowns, which are A1 and A2. And if you do that, you get A1 and A2 equal to, so A1 minus 0.05018 Q over EI, A2 equal to 0.000241 Q over EI. And then, once you have this, you replace in your approximation function, and you will have your approximation function equal to, so Q over EI is equal to 1. Q is 1,000, EI is 1,000. This becomes 1. So you get minus 0.05018 x1 minus x plus 0.000241 x squared times 1 minus x. This is your approximation function. As you can see here, is a function of your x coordinate, and you can get the deflection of the beam for all x coordinates of the beam. And I did plot this for you, comparing the analytical solution or the exact solution with what you see in this plot is the deflection of the beam. So in this axis here, you have the longitudinal coordinate x from 0 to 1. In the vertical axis, you get the deflection of the beam. The dots are the analytical solution or the exact solution. the dashed line is when you use Galerkin method with only two terms, which was what we did. You can see there is some small error here at the midpoint of your beam when you compare with the exact solution. But if you do the same analysis considering now four terms for your approximation, or four shaped functions, or if you refine your mesh in FEA, is equivalent. If you refine your mesh, or if you use more terms in your approximation function, you can see that you get a coincident result, almost coincident, right? With your exact solution, right? Okay? So, we are going to finish here. Next week, we are going to apply this Galerkin method to our beam, and we are going to start the air elasticity, divergence, all right? Static divergence of the wing. Okay? Sorry for this, but I think it's important for you to understand these things, right? See you next week.